Now, I just want to tie everything we talked about in this lesson together. System delay. You've got an input, gets processed by a system, and you have an output. It's useful to talk about what the delay is for a system. I'm going to describe what I intuitively think about when I hear the words system delay. Just to make it easier to draw, I'm going to draw as if it was continuous time, but realize that this is discrete time. We've got some sort of input here, and all of a sudden it does something big, and that's my input. And I kind of expect that my output is going to do something, and then it's going to have a kind of response. And it may look different than my input, but there's going to be some sort of delay between here. And that delay is what I think of when I talk about my group delay. Now, given what we did in our previous slide over here, when we talked about the system phase response, what this seems to suggest is that if our system has a linearly decreasing phase, well, then we know what that delay is. We just simply take the negative of the slope, and that's our delay. But what if our phase isn't that simple? What do we have then? What if our actual phase looks something like this versus frequency? Well, the way that we can approximate our group delay is it's going to be a difference depending upon what frequency we're looking at. But if we say it's equal to minus the derivative of our phase function versus omega, that's just a fancy way of saying, what is its slope at any point? In other words, at omega equals 0, it's this slope. At omega equals whatever that point is, it's this slope. And we can see that although the slopes are different, they're all approximately. And so in the special case where we have a system with a linear phase, then this derivative is exactly equal to this slope, and it's exactly equal to how big this delay is. And in this linear phase thing, I would expect my green to look exactly like my red, just simply delayed. So here, our group delay defined to be equal to minus the derivative of the phase function with respect to omega. But in this particular case, it's just going to be if our theta of omega is equal to minus k times omega, it's just going to be equal to k. Now, here's the flip side. We talked a few slides earlier about two types of transfer functions. One that has an order of 0, no feedback, finite impulse response, and the other with feedback, order greater than 0, infinite impulse response. Here's an interesting fact. This lowercase can only be true for FIR filters only. Only FIR filters can be linear phase, which means only FIR filters can have a constant group delay, meaning only FIR filters will delay all frequencies by the same values, the same number of samples. Now, it's possible to design an FIR filter that does not have linear phase. I'm not sure why one would do that. That would be Now, not all FIR filters have linear phase, but if a filter has linear phase, it has to be FIR. In other words, linear phase means it must be FIR, although FIR does not necessarily mean linear phase. Now, if it has a nonlinear phase, all IIR filters, infinite impulse response filters, have non-linear phase responses. And that means all IIR filters have non-constant group delays. The group delay is a function of frequency, and the amount of group delay depends upon how much frequency you have. It might move low frequencies more and high frequencies less in the time domain. And that means that since they delay different frequencies, different amounts, these must necessarily change the shape of signals versus the FIR filters that, if they're linear phase, do not change signal shape. So these are the walk-away lessons, is that if you want to see how much a particular system delays a input signal, you just take negative times the derivative of the phase response, and that tells you how much it delays. And if that delay is a function of frequency, then you're probably looking at an IIR filter, which all of them have nonlinear phase responses, and that means their group delay changes depending upon what the frequency is, and that means it changes the shape of the signal. For FIR filters only, it's possible to design FIR filters that are purely linear phase, and that means their group delay is constant among all frequencies, and that means all frequencies are delayed by the same amount in the time domain. Linearly increasing amounts of phase in the frequency domain corresponds to same amount of delay in the time domain, and that means if your FIR filter is linear phase, it does not change the signal shape. And that's obviously a big thing if you're designing a filter. You'd like it to not change the signal shape in the passband, and you'd like it just to stop the entire signal in the stop band.